So we want to describe geometry actually, because we said that we want to have some solution for the Einstein's equation that will lead us to the case of the vacuum solution. But the question is how to describe a geometry. And then the idea is that we can describe geometry by describing the distance. And this is related to something that we learned long ago in elementary school, that we have the theorem of Pythagoras. So if you have this triangle which has a 90 degree here, then this length of the longest side squared is the sum of the square of its sides. So by this property actually we can describe any distance in space. Our well-known two-dimensional or three-dimensional space, because we can consider the Cartesian system, for instance, the two-dimensional Cartesian system. So we can ask ourselves, what's the actual distance? And then we can just see from the picture that actually this side is just difference of the x coordinates of those points, and this side is actually just difference of the y coordinates. So the distance of these points is actually just, again by the application of the same theorem, or for convenience we can also of course write it like this. So this is when we have some distances in plane. So when we have a two-dimensional normal geometrical space, which describes the usual kind of geometry on which our everyday life experience is based. When we have a three-dimensional geometry, so space which is not just concentrated to a plane, but general geometrical space, then it's simple to extend this equation. You just add the z component in the Cartesian coordinates. So this is actually just the description of space. So our normal, we call it Euclidean or flat space, the space of our everyday experience, the space for which we studied all those geometrical theorems and properties back in school days. This is actually the space which follows this rule. So by setting up this rule, we have defined the space. We can say that all the necessary information about this space is actually contained in this rule, which gives us the distances between points in this space. And this is actually the point where we can understand what is going on in general relativity. Since two things happen. First, space and time becomes connected. So here we have only space in this classical Euclidean space. But in general relativity we have space and time. So that means when we go from this normal geometrical space to the space-time of general relativity, we will have some equation for the distance of points in this space-time, but there will also need to be a time involved there. That's the first difference. And the second difference is that that space can become curved. That means it doesn't have to be as simple as that all of those coordinates are just squared, and all having the same coefficients. They can have different coefficients multiplying them, and they can all be functions. So things can become quite complicated here. But the idea is that, again, if you prescribe a distance between points, then you actually describe the geometry now of the space-time. And if you want to study black holes, that means that you need to describe this geometry of the space-time which describes that black hole. And we said it is a solution of Einstein's equation in vacuum. That means this type of geometry, which is defined by this formula for the distance, will then be in accordance with Einstein's equation. And this type of geometry will then actually contain a black hole. And that is how black hole emerges. So, this is good for flat space-time, but this is not the solution of the aforementioned Einstein's equation in vacuum. But the following is. So here is the real solution. I will explain in detail what does this mean. But now, at this point, I just want to say that when you put this type of a distance function into the Einstein's equation in vacuum, they will be consistent with this demand that this mathematical object vanishes. So this is actually representing how does the geometry of a space-time in vacuum looks like. And what does it mean? What does it mean? So you can see the idea. The idea is the same as for the old usual Euclidean space without time, which is not curved. You have this relationship between coordinates. But now there are some changes. So you see here we use delta to label the difference between the coordinates. Here we don't use delta, we use this d. And this d stands for, actually, it is not very strict, but it will give an idea and a picture of it. The differential difference. So it is not a finite difference between points, but it is a difference which becomes arbitrarily small. Because when we have arbitrarily small differences, that means we covered all the points in some space-time. Because if I want to describe space-time by the difference and distance of these 2 points, then maybe there can be some hole in between those 2 points. So I did not completely describe it just by using a finite distance between coordinates. But if I make the separation smaller and smaller and smaller, so there is no other point between the 2 points, so to say, then nothing is skipped, and we have just covered all the space-time. So this is somehow we can intuitively say the logic behind this. So we go to this, which you can intuitively imagine as a very small distance. So this very small distance and very small distance. So that's one thing. But it has essentially the same logic, that it represents a distance between points in space-time, this d appearing here and here. So here, time now enters. Before, of course, we didn't have time because it was just the standard flat Euclidean geometry. Here we have space-time. So there is this time coordinate which I mentioned that it will enter in. So we have it appearing here. And we are now using different sets of coordinates. We are not using Cartesian coordinates, but we are using different coordinates, the ones that are quite proper to describe spherical symmetry, the spherical coordinates. But this is not of our main concern. Our main concern is just to give the basic idea. So this L just means a radius. A radius in the same sense that you have a radius of a sphere, or radius of a circle, or anything like that. So this R represents always a radius. Like you have some geometry and then you use a radius as your parameter to describe where you are. So you see, there are time and radius, which are both entering into the equation for the distance. And that is actually connected to the very fact that we are dealing with the space-time. You don't have just space or just time. You have time and you have space, and they are connected inseparably in the same equation. Then you have one part which is describing the angular part, which we can now just skip for the time being. It is not of interest to us because it does not show what is going on. It is not specific for a black hole kind of approach. So we actually focus on those two terms. G is again this Newton constant of gravity, and M represents the mass. The mass which is creating this space-time. So it is a vacuum solution of Einstein's equation. There are no other masses, but there is a mass which created this space-time, which is empty in any neighborhood around that mass. To speak about black hole, it is not something mystical, something that came from some very deep philosophy that we cannot follow or anything like that. So the black hole is actually just what I wrote here. So the black hole is just a specific type of a solution to Einstein's equation. It is just a specific type of relationship between space-time points in the equation for the distance.